Hello, this is Dr. Muhammad, and this is another video under Dynamics of Structures for Multi-Degree of Freedom System. And today I'm going to talk about an example on modal expansion of displacement. So we are going to take an example on what we have explained in the previous two lectures. So I hope that you watched the previous two videos before going into this video, because it is really building upon them. Okay, so we are going to have an example, as you can see here. In this example, we are going to clean here. So in this example, we want to determine the vibration response of the two-story shear building, shown that you can see it here. It has 2m in the first floor and m in the second floor. So we have like double of the mass, 2m here and 1m here. Okay, and we want to know what is the vibration response, as we said. This means that u of t, or we can see the vector of displacement at any time, because we are dealing with any time, or we are interested in any time here. Okay, this is due to what? Due to initial displacement u node equal to minus half and 1, and this is something similar to this, which is half and 1. This is the initial condition displacement, This is u node. This is u node. Okay, so we need to know what are the mode shapes and what are the eigen value for our system. And remember well that commonly the amplitude, or the modal amplitude, or the mode shapes, and the eigenvalue, or the natural circular frequency, they are supposedly to be in our hands, okay, before starting, or for the solution, before start the solution. So we have phi 1 and phi 2, which is the first mode shape and the second mode shape. It is given for us. It is half and 1 and minus 1 and 1 here. It is similar to the previous example that we have worked before. And omega 1 and omega 2, they are already we have calculated them before. If you do not know how we can obtain phi 1 and phi 2 and omega 1 and omega 2 for this simple example, please revisit 3 videos before, or maybe 4 videos before, and you are going to find full explanation for how to extract the natural period, or the natural circular frequencies, and the normal modes, or the mode shapes of the system, and or a similar one. Okay, so this is actually what we are going to have here. Okay, so let's clear, and let's move on for our solution. Okay, so let's go to the solution for our example. So first of all, we need to know that we need like 3 different solution steps. So we are going to have 3 different solution steps. First of all, we need to calculate Q1 node and Q2 node. So we have Q1 node and Q2 node, which are the effect of the initial, as we said before, initial displacement vector. So we have, this is the contribution of the initial displacement vector, and then we are going to have, or to calculate, Q1 dot node and Q2 dot node, which is the contribution of the initial velocity vector. The contribution of initial velocity vector. And remember well the designation of each thing that we are putting here. Q1 and Q2 means that for mode shape 1 and mode shape 2, and between parentheses 0 means that it is at t equal to 0, means that at the initial condition. In a similar fashion for q1 dot and q2 dot, dot means that it is for velocity. We are talking about velocity, not displacement. And 1 and 2, it is mode shape 1 and mode shape 2, and between parentheses 0 means that we are talking about t equal to 0, which means that initial condition. Okay, this is the initial condition. Okay, so now let's go to the next part, which is related to the calculation of qn node and qn dot node. So we have the two here, qn node and qn dot node. So whenever we are talking about qn, this is related to the displacement. So we're going to find in the equation, this is from where? From equation 9. From where equation 9? This is in the previous lecture, you can find it, okay? But anyway, this is how previous how equation 9 is providing us. So as we said, this modal coordinate is going to be known if we know three things. First of all, the mode shape, including this one, and the second is the mass matrix, and the third is the initial displacement vector, u node, as because we are going to have this initial displacement vector. We are going to have initial displacement vector. So the contribution is going to be based on that. We have in our hand the initial displacement vector. It's supposed to be given for us, right? Okay. On the other hand, equation 10 gives to us qn dot, which means that velocity contribution here at t equal to 0. So we are going to have this part here, which is, or this vector, which is u dot, no, the initial velocity vector. Initial means that t equal to 0. Velocity, it means that u dot, as we know here, and it is a vector because we are talking about different multi-degree freedom. Similarly, also we need to know that we need to know the mode shape, mass matrix, and this initial velocity vector. Okay, from where we obtain this or these equations, please revisit previous video. Okay, now let's clean this and move on for something else. So this is step number 1, or this is the first step in the solution. After knowing qn node and qn node dot, then we are going into the next step, which is we are going to calculate q1t and q2t. So now what is the difference between this, okay, and what we have obtained before? This modal coordinate for specific time, at the initial condition. But this modal coordinate, it is at any time. It is at any time that we like. So q1t and q2t, it is the contribution of the first mode shape, and this is the contribution of the second mode shape, okay, which is the modal coordinate. And each one of them, if you remember, and I have mentioned this before, each one of them, whether q1 or q2, it gives us two components. One component related to the contribution of the displacement vector represented by qn node, and the other term is going to be the contribution of the velocity, the initial velocity vector, which is going to be qn node. So every term is going to be, or this q1t, it has always two things, two parts. One related to u, okay, which is u node, and the other is related to u dot node. This is for both. But here this is q1, this means that the mode shape number 1, and this is for mode shape number 2. But we have two contributions, okay? We have two contributions from the initial conditions for displacement and for velocity. Well, that's very fine. From where we can obtain q1 and q2? It is from equation 12. From equation 12. Let's clear here and move on to see. This is equation 12 here. This is equation 12. And as you see, q and t, It has two parts. One part, one term, and another term here. One term contains qn node, the other term contains q dot n node. The first term, it is cosine omega nt, the second term is sine omega nt, and do not forget that we are dividing by omega n. So what is, as I said here, this is an important, this is the contribution of the mode shape, or the contribution of the initial displacement vector and the initial velocity vector through the first mode or the second mode to the total response that we are going to have. So at the end, we are going to see, this is the second step, obtaining q1t and q2t. Well, if we got them, what is the next step? The next step is the final step, which is u of t, the total response, which is the total response at any time t for the first degree of freedom, and the total response at the second degree of freedom at any time t. So u1 here means that at degree of freedom 1, this is degree of freedom 2. And t means that at any time. Okay? And we're going to use what? Equation 11. Here, this is equation 11. And we mentioned that before, based on the modal expansion, as we said. So our total response is going to be the summation of the mode shapes. Every mode shape is going to be multiplied by like weighing factor. We call this the modal coordinate. And this modal coordinate qnt, already we have obtained it from step number 2. Already it is obtained from equation number 12. So we are going to have the contribution of every mode, and we are going to have the contribution of the initial displacement vector and the initial velocity vector within or from within this qnt. Then everything is going to be given for the final solution for us. Okay, so I hope that you understand what. So as I said, our steps for the solution. First, we are going to calculate the modal coordinates related to initial displacement vector and initial velocity vector. After that, we are going to calculate q1t, which is the modal coordinate at any time related to mode shape 1, and modal coordinate at any time related to mode shape 2. And the last thing is to obtain the total response, which is going to be u1 of t and u2 of t. And based on that, we are going to have the final response, which is the summation of all mode shapes. Every mode is going to be multiplied by qn of t. And we said this qn of t, we can obtain it from equation 12 from the previous lecture. And we said that it has the two contribution of initial displacement vector and initial velocity vector. Okay, now let's go to the next part and see how we can understand more. So step 1, as we said, this is step 1. In order to calculate qn node and q dot n, we need, yes, in order to obtain qn node and qn, I think this is node, just a second. So qn node and q dot n node, we need to know u dot node, right? U dot, which is the velocity. Okay, this is for equation number 10. So u node, which is the initial displacement vector, it is given for us. So here we are going to find that half and 1, as I said, it is given. Initial displacement given, or it is commonly it's supposed to be known for us, and we found them, they are constants. So in order to obtain u dot node, we're going to derive this. As we can see, they are constants. This means that the initial velocity vector is going to be a zero vector, right? Because we have constants here, so we do not have any time, for example, or anything related to the variable. This is constant, so we are going to have our initial velocity vector is going to be zeros as well. So why we are obtaining this? Because we need to obtain, in order to obtain Q dot N node, we need to have in the equation, if you revisit equation 10, you're going to find, let's get rid of this. Okay, in order to get equation 10, then we are going to find we need here U dot node to be obtained. So it is the initial velocity vector, So this is to obtain, as I said many times, Qn dot. It is the contribution of the initial velocity vector through the mode shape itself, okay? And Qn node, it is the contribution of the initial displacement vector through the mode shape under consideration. This is equation 9 and this is equation 10. Please revisit previous lecture to understand from where we got these modal coordinates. Okay? Okay, so now we obtain this U dot node, and then everything is known for us. If you look here for equation 9 for Qn node, the mode shape amplitudes are given. We know phi 1, right? So it is given for us. Mass matrix, it is known for us. We know masses and the degree of freedom 1 and degree of freedom 2, it is given for us. And U node, it is given for us also. So now everything is known here, okay? The numerator and denominator, then we can get Qn node. In a similar fashion, we can obtain Q dot N initial, or for node at t equal to 0. Everything is known regarding the mode shape, and the mass matrix is okay for us, and in the same time we have U dot node, it is 0. Okay, vector of 0, the initial velocity vector, right? Let's clean here and let's move on to see what next. So now let's calculate what we have done. This is equation 9 and 10. So we have Q1 node, we're going to calculate it, and then Q2 node, we're going to calculate it. Okay, this is for mode shape number 1, this is for mode shape number 2. So first of all, we put phi 1t, which is the modal amplitude vector. It is transposed, so we put it in this form, as you can see here, half and 1. Okay, similarly, directly we can go to the denominator and put it the same, so we're going to repeat it here, and then we're going to put it here but without transpose, okay, as it is. That's it. Mass matrix, we know how to compose this mass matrix before, as we have explained before. On the diagonal, we are going to put the masses 2m for the first degree of freedom and 1m for the second one, similarly here. And then the only thing is this, which is U node. This is the initial displacement vector, half and 1. It is given for us. It is given for us. If you are going to calculate this half, 1, and so on, if you are going to calculate this, you're going to get it at the end 1. Please calculate it and check it. Okay, we're going to obtain here 1. Okay, then let's go and repeat the same for the second mode, Q2 node. We're going to put here exactly phi 2 transpose. So this is mode shape number 2, minus 1 and 1, as we know, minus 1 and 1, and here minus 1 and 1. This is mode shape 2. Mass matrix, the same as before, and then we are going to put the same initial displacement vector. If we put this, we are going to find that we have zeros. It's going to bring us 0. Try to calculate, you are going to find that it is 0 here. So this means that Q2 node is going to be 0. What is the meaning of this? Exactly. The distribution of, or the contribution of, the initial displacement vector through the second mode shape is going to be 0. There is nothing. Okay? I hope that you remember this. This is only a kind of a reminder for us. This is, remember this. Okay? Remember that QR, what is the meaning of QR? Because maybe we miss the meaning. It is a scalar multiplier. Okay? We call it modal coordinate. It is multiplied by the mode shape to get the sum Do you remember the sum? The sum of the total responses, as we said here. So we said, as I give it as an example for 3 degrees of freedom, U1 and U2 and U3, if we're talking about T, for example, here. So it is going to be first mode times Q1, scalar quantity. Mode shape number 2 times Q2, scalar quantity. Mode shape 3 times Q3. So they are like, as I said, they are scalar multipliers. Scalar multipliers. So whenever we have Q2 here equal to 0, this means that the contribution of the initial displacement vector from the mode shape number 2 is going to be 0. It is not going to contribute. Okay, it is not going to contribute. That's clear. Move on. Okay. Now, in our example, as you can see here, we have Q1 equal to 1, Q2 node, of course, it is 0. Then we're going to calculate, okay, this is already we have Q1 equal to 1, Q2 node equal to 0. What is the meaning of this? Again, I'd like to place emphasis upon the basic principle so that do not lose the base or the main understanding of what we're doing, okay? So Q1 node means the initial displacement vector affects the total response considering the first mode or through the first mode. That's the meaning of Q1 node. And Q2 node equal to 0, this means that the initial displacement vector, again remember this word, displacement. I'm talking about displacement here. The initial displacement vector will not affect the total response considering the second mode or through the second mode. Okay? So this is the meaning. This is the meaning. From Q1 node and Q2 node, okay, in a similar fashion we can obtain Q1 dot node and Q2 dot node, both of them. How we can obtain them? Exactly, it is the same as we have obtained Q1 node and Q2 node, but instead of this we are going to use U dot node, the vector, the initial velocity vector. But we know that this vector equal to what? 0 and 0, right? So this means what? Let's erase here everything. Go up. So in this equation, instead of Q1 node, we're going to put Q1 dot node. And everything will be the same, but here we're going to put the initial velocity vector. It is going to be 0 and 0. So everything is going to be 0. In a similar fashion, Q2 node dot, if we put dot here, then everything is going to be the same, but here it is going to be 0 and 0. So it will be 0 also. So this brings us to the point where that Q1 dot 0 and Q2 dot 0 equal to 0. What is the significance of this, the meaning of this? This means the initial velocity vector will not affect the total response, considering both here, the first and the second mode shapes. Can you understand this? This means that whenever Q1 dot and Q1 dot and Q2 dot nodes, this means that the initial velocity is not going to affect anything. Because really it's right, initial velocity vector is 0 and 0, so it will not affect anything. Whether through mode shape 1 or mode shape 2, it will not affect anything. So it is quantified here through this Q1 node equal Q1 dot node equal to Q2 dot node equal to 0. Okay, let's clean and move forward. Okay, so let's go now to step number 2. Let's go to step number 2. Okay, so here in our step we said that from equation 12 clean here. So from equation 12 we can obtain Q and T. Remember, it is Qn what now? T. Remember, there is a difference between Qn node and Qnt. Node, it means that initial condition. T, it means that at any time. Modal coordinate at any time due to specific or particular mode shape. Okay, so in this case we are going to have Qn of t is going to equal, this is we have explained before in the previous lecture. We said that it has two terms, one term containing Qn node and the other term is containing Q dot n node, and the remaining part is related to the sinusoidal function with considering also omega n, which is the natural circular frequency of the mode shape itself. So it has the contribution from both parts, initial velocity, initial displacement vector represented by Qn node, initial velocity vector represented by Q dot n node, the natural circular frequency of the mode shape, and the sinusoidal function. This is equation 12. If you don't know how we obtained it, please visit the previous lecture. Okay, now let's go and get Q1t and Q2t. If you look here, we're going to put it Qn node, it was how much? 1. We calculated from the previous slide. Times cosine omega 1t, because we're talking about mode shape number 1. So 1 here means mode shape number 1. T means that at any time. T means that at any time. T means that at any time. Okay, cosine omega 1t plus Q1 dot node, it equals to exactly 0 over omega 1 over omega 1 times sine omega 1 t. As you can see, this is 0, so all of this term is going to be cancelled. We're going to, the remaining part is 1 times cosine omega t here. So Q1t equal to 1 cosine omega t. At any time, the contribution of the initial condition is going to be from mode shape 1 is going to be cosine omega 1t. That's it. I mean that it is going to be only this one here. The other part, other term already vanished, and we are going to remain with the cosine omega t only. Okay. The second part, which is related to the mode shape number 2, Q2t. So the contribution or the modal coordinate at any time due to mode shape number 2. For what, or for the sake of what? This is for the sake of the total response. So when we substitute in the equation, Q2 node, found it how much? It was 0 before, right? Cosine omega 2, it is already 0. And Q2 node, we said that it is 0 also. So all of these terms are going to be 0. And then we're going to end up with Q2 t equal to 0. Q2 t equal to 0. What is the meaning of this? Let's move on and read this. Here the meaning is, this means that the second mode shape will have no effect on the total response vector u of t, okay, of the system, because Q2 at any time, the contribution of the second mode at any time would always be 0. The modal phi 2 is going to be multiplied by QR. Do you remember? This Q2 t at any time is going to be 0. So the mode shape is not going to work for us. This mode shape is not going to work for us. Okay? So let's clean and move forward. So here, step number 3, it is going to, so now we obtained everything. We obtained Q1, and we know that it equals cosine omega 1t, and we know Q2t, and we know that it equals to 0. Then the next step is to go, step 3, to calculate the total response. So this is what we call it, the total response, which is going to be composed of 2 different modes, mode 1, phi 1, and phi 2, right? So we're going to use this equation, which is equation 11. In equation 11, we see that any mode shape, or not any mode shape, this is the total response, which is any vector can be represented by a set of n vectors multiplied by the modal coordinate here. You remember this? This is the modal expansion displacement concept that I have explained 2 lectures before. Okay, any vector in the world, you can represent it by other n different n independent vectors multiplied by modal coordinate, scalar multiplier. Okay, so we can get it now that the total response, this is the total response. Okay, the total response, it equals to 2 parts. One part related to phi 1 or mode shape number 1, and another term or another part related to mode shape number 2. We find phi 1 here multiplied by q1t, and we can find phi 2 here multiplied by q2t. We realized, or we obtained, or we have known now that q2t equal to what? 0. Right? So this means that this term is going to be, it would vanish, it would cancel out, right? And the remaining one is going to be phi 1 times q1t only. The contribution is going to be from mode shape number 1. No contribution from mode shape number 2. That's it. Okay? Okay, so this means that we can end up here with that the total response u1 at degree freedom 1 at any time and u2 at degree freedom 2 at any time equals to half and 1, which is mode shape number 1, times cosine omega 1t, which is the modal coordinate corresponding to it. What is the value of omega 1? It is given for us in the beginning of the example. It equals to the square root of k over 2m. K over 2m. Okay? I hope that we have understood now. Let's go to the next part. Let's clean everything and then let's move on to the next part, which is the final part for it. Where I'm going to give some notes about the example. This example is very important actually, because it gives us an important understanding that sometimes we forget, that not all modes, first and the second, not all mode shapes are going to contribute and control in our total response. So the first mode shape controls the total response because q1t, it has cosine omega t. So we have contribution for mode shape number 1. However, the second mode shape has no contribution to the total response u of t. It has no contribution. Why? Because the modal coordinate at any time qt equal to 0. So this means that the second mode is not going to affect us. Okay, the question now is why? Why this happen? Okay, why this happen? You can pause the video here and please try to think about this. Why that the first mode in this specific example is giving us something and q2 or the second mode effect is not there. It is going to be 0. Pause the video for 5 seconds and try to think about it. Okay. If you look to the initial condition from the beginning, okay, in the initial condition, let's clear out here. In the initial condition, I said to you that u node equal to what? Do you remember? Half and 1, right? Do you remember what is the first mode shape? The first mode shape. It equals what? Exactly, half and 1 also. It is only coincidence, okay? It is by chance we found that they are the same. But actually it's meant to be actually like this. We want the mode shape number 1 to have the same initial displacement vector here. Because of this, I'm going to explain it graphically in a minute. So because of this, we are going to find that this mode shape, first mode shape, is going to have contribution. Actually, it is going to have the only contribution, while the second mode shape is going to be orthogonal to it. It would not affect the motion at all, because all the initial displacement vector, it is proportional to the first mode shape. Okay, so we can put this like this justification in this way. This is because the initial displacement vector U node that we have given in this example equal to half and 1 is proportional, this is the key word here, proportional to the first mode shape, which is phi 1 half and 1. It is proportional to it. They are actually identical, right? And hence it is going to be orthogonal to the second mode shape. The second mode shape will not make anything. It is not going to make, because I initiated the system with half. This is the system. I initiated it. Okay, I initiated it with half and 1. So already the system is initiated with the same shape of the first mode. So the first mode is going to have the major contribution here. Okay, so this is an important thing that we need to take into consideration. Okay, so we need to take into consideration this difference between how we can put U1 and U2 into the spot based on the initial displacement that we are, initial displacement vector that we are using. Let's clean up here. And let's show it graphically for you. I hope that you can. Yes, let's have it like this. So it is going to be, yes. So now we have, this is the first mode. This is the first mode. Look at the first mode, how it looks like. We have like 2m here, and we have m here, and we have half in the first degree of freedom. This is the first degree of freedom here. Okay, DOF1, and this is DOF2, right? And we have, this is half and this is 1. This is the first mode here, half and 1. And for the second mode, if you remember, it is given for us -1 and 1. Let's put it graphically here. -1 in the first mode, as you can see, this is -1. Yes, this is, I think that I should, yes, put it in the other form. So just a minute, I think that, so we can, not sure I'm recording or not, but I think that now this is the contribution of the second mode. So as you can see here, this is the second mode. We have like -1 here and +1 here. So if we are going to put it, we're going to find that this is -1, means that if we say that this is the positive direction and this is the negative direction. So in this case, we are going to have, this is -1 and 1. So the final is going to be, let's clean and move on a little bit. Okay. So I think that here, yes. Okay, so here, as you can see, the first mode and the initial displacement vector, they are the same. So this means that the contribution of the first mode is going to be the dominant here, not the second mode. The second mode is not going to be there. It is going to be, it is not going to be dominant as the first mode. Okay, so this is why, because the initial displacement, as I said, vector is similar to the first mode. Let's clean here, and that's the end of this video. I hope that you have understood it well, and I hope that I have explained it in the right way. If there is something not right, I think that maybe I put some or if there is some mistakes, for example, I put here and there. So please let me know in the comments so that I can correct. Okay, that's it for today. Thank you, and see you next time.